Right, so chemistry was the study of matter. You can see this is going to be fun already. Let me put that just a little bit of a twist. So chemistry was the study of matter. Matter is anything that has mass and takes up space. The units, a word that identifies the particular standard of measure that's being used. If we're using meters or liters or feet or miles, it's the word that defines that particular standard that we are using. Now the metric system, it's just one system of standards. So feet are part of the English system, meters are part of the metric system, as are liters and grams and so on. So this metric system is a system of standard units. Mass is a measure of how much matter makes up an object. What's my technical term for matter? Stuff. How much stuff is there? So when you take the mass of something, you're measuring how much stuff, how much matter makes that object up. Weight is a measure of how much force gravity exerts upon a given mass. You and I might have the same amount of stuff here and on the moon, but here on Earth we weigh different than we would on the moon, even though we have the same amount of stuff. So weight is a force. It's key thing to remember. Weight is a force. Mass is a measure of the amount of stuff. You have a higher weight when you have more mass, but they're not exactly the same thing. They're different things, which is why the Newton is the metric system's standard unit of weight. A Newton is a force unit. A Newton says how much force, basically the force of your weight in the metric system. So you'd have to take mass and convert it to newtons to know what the force is. Volume, a measure of how much space an object occupies. The beach ball, when it was small, we blew it up, it took up more space, more volume, because the air was inside of it. And the Factor-Lable Method, it's a method that we use, or it's a process of steps, is another way to think of it, that uses relationships to convert a measure into another measure. So we got something, we need to convert it into another language. Past years I've referred to this as kind of like the Rosetta Stone of the process. You know, you're all familiar with what the Rosetta Stone actually is, right? Have you heard of it before? Okay, so the Rosetta Stone was the key of allowing us to translate between different ancient languages. It provided us the same text in several different languages, and so once we had it in one language, we said, oh, that's what that means in that language. Oh, that's what it means in Greek. That's what it means in Egyptian hieroglyphic. It helped us fill in the gaps of, well, how do I understand the same thing in a different language? What we've done so far is use the Factor-Lable Method to convert from one language, one standard unit, to another language using another standard unit. Same thing, just a different way to represent it. We're going to do more of that, some more complex conversions like that today. We're also going to use this method, the same process, repeatedly throughout the entire course. So it's real important that you kind of understand this Factor-Lable Method, the thought process that it takes, because you're going to use this not in every module, but you're going to need the concept in every module, and you will use it literally in multiple modules throughout the entire course. So we're going to spend a good bit of time on it. Here's the first table. Centa and kilo, lowercase m, lowercase k, they're all lowercase, and then what their meaning is. 1,000th, 100th, and 1,000. So it's mass. This is where the slug came in. The metric, or the English unit of mass is a slug. In the metric, it's grams. Distance, you had to know meters and feet. The volume, liters and gallons. And time are both in seconds. All right, so we are going to go back to this idea of converting between units using the Factor-Lable Method. So again, on your notes, we are still in section 5 of the first module. Module 1, section 5, converting between the units using the Factor-Lable Method. In a few slides, I'm going to start changing the terminology a little bit on us to kind of move us past this idea of given and wanted. But remember, the Factor-Lable Method is a way of converting between something that's given to you and something that you want. A language it's given to you in and the language that you want it to be in. And those languages are the different units. And that conversion factor, later on I'll just abbreviate this as CF, but the conversion factor comes from a statement of equality. Now remind me, what's a statement of equality? What does it look like? Statement of equality is just, looks like a formula. It looks like if this equals that, A equals B, or A equals C. It's a statement that has an equal sign. This equals that. That's the statement of equality. And remember that we talked about the concept that if I have a statement of equality, two things that are the same thing, in math we've got this concept that if I divide anything by the same thing, the value is 1. That's how the conversion factor works to translate. One quantity and another quantity are the same thing. So in terms of identity, it's the same thing. Whatever we had, we're multiplying by 1, but we're translating it. Remember, we use the idea of dozens. 1 dozen is 12 pieces. So if I have 12 eggs, or I have 1 dozen eggs, that's the same thing, right? So conceptually, if I divide 12 eggs by 1 dozen eggs, I haven't changed it. It's the same thing. It's 12 over 12. It's 1 over 1. I mean, all I've done is change the units, and that's the concept we're working with here. So when I'm given a certain number of units, my conversion factor right in here is going to be the statement of equality with my wanted units divided by my given units. And the idea being here that, and we're going to get more into this probably tomorrow, but we have to work the units as well as work the coefficients. When we do math and chemistry, we're as much concerned about the units as the numbers. Remember we said that a number without a unit has no meaning? It's wrong, because everything is identified with a unit. We do have a particular ratios, some mole fractions and things like that we'll talk about later in the course that don't have units, but I'll say virtually everything has a unit associated with it. And so when we do the math, we actually do the units portion and then we do the numbers portion of our math, because we handle units just like we handle numbers. We multiply units, we divide units, we do math on the units, and then we do math on the numbers, and then we combine the two in the solution. So what we're doing here is we're saying I've been given some measurement in a certain language, a certain unit, and I want to get it in a different unit. How do I convert it? I convert it using a conversion factor. Conversion factor comes from a statement of equality. This equals that. And when I'm going to arrange it, I'm going to arrange it in such a way that what I want to end up with in the end goes on top in my numerator, and what I was given goes in the bottom in my denominator. What that does, remember, is whatever units I'm given is going to cancel whatever units are given. I'm going to be left with the wanted units, and that's going to be my answer. We'll walk through a few of these together. So the example we had was converting pieces to dozens. 1 dozen is equal to 12 pieces. So if I want to go from dozens to pieces, or excuse me, if I want dozens, well, I will have the number of pieces times my conversion factor. 1 dozen equals 12 pieces, but it matters whether I have 1 dozen on top or 1 dozen on the bottom, the numerator or the denominator, excuse me. I have to have what I've been given, pieces. That number and that unit has to be in the denominator in the bottom, so that pieces will cancel pieces and will leave me with dozens. I'm looking for dozens, and if pieces cancels pieces, I'm left with dozens. My units are right. Now I'll go through and do the math with the numbers and plug that number, that coefficient, in front of the unit of dozens. Same thing can be done with pieces. The number of pieces, if I'm given dozens, is dozens times pieces divided by dozens. And mathematically, hopefully you see that dozens will cancel dozens, and I'll be left with pieces as my final units. Since I'm looking for pieces, my setup is correct. Since my units are pieces, now I'll go through and do the math on the coefficients. So we'll work a few examples. Let's look at on your own 1-1. That's on page 12 in your book. Let's walk through this concept. Let's apply the given and the wanted. And I'm going to start referring to them as the known and the unknown, because that'll work for us better in the long term. So slowly over these slides, it'll transition from given and wanted to known and unknown. Matter of fact, on this first slide on your own, I start this transition by saying here, we're given something, that's our known. Let's read the problem. A student measures the mass of a bag of sand to be 9,321 grams. What is the bag's mass in kilograms? So first thing I'm going to write on my paper is given. Or if you want to kind of move ahead, write down the known. What's known? The known is that I have a mass of 9,321 grams. Okay? That's my known. Looking at the problem now, And I know word problems can be difficult for folks. Even if you can do the math, sometimes taking English and converting it into a mathematical problem can be difficult. So look at the problem. What's the next thing? I've got a known and I need an unknown. Something I'm solving for. What's something I'm driving to? What does it say? Well, student measures the mass of the bag to be 9,321 grams. That's my known. What is the bag's mass in kilograms? That's my unknown. My unknown is my mass in kilograms. All right? So I have a known mass of 9,321 grams. I've been asked for the mass in kilograms. So what's unknown? What is that mass in kilograms? I have a given times a conversion factor to go to my wanted units. I have, maybe another way, I have known units, and I need a conversion factor to take me to my unknown quantity of the unknown, of the wanted unit. Okay? So how am I going to set this up? Based on the model I've shown you already. What's the first thing I'm going to write over here? Go ahead.
The given, which is 9,321 grams.
Okay, that's good. Before we get there, there's one more step that I've shown you thus far, or so far. What's the conversion factor going to be, right? I know that I'm going to have a given times a conversion factor to get to the wanted. Yes, sir?
1,000 grams equals 1 kilogram.
Right, 1 kilogram. 1 gram could be written as 1/1000th of a gram. That's the way my mind works. But technically, just to keep it simple for now, you've learned the prefix table, right? You've gone through and memorized that. So I'm looking for something in kilograms. My base unit is grams. So my conversion factor is going to come from a statement of equality that says 1 kilogram is equal to 1,000 grams. It would be correct to say that 1 gram is equal to 1/1000th of a kilogram. That's true too. But just keeping it simple for now, you guys have memorized that kilo means 1,000. So it's 1/1000 grams is the same as a kilogram. So that's true. And since it's true, it truly is equal, we can use that to create a conversion factor. So we can take our given, like Austin already started to tell us, we can take the given times whatever I want it to be in divided by what I've been given based on my statement of equality to get to what I want. So you said 9,321 grams times a conversion factor. What unit has to be in the denominator, in the bottom? It's got to be grams, right? Because I'm trying to get rid of grams and put it in the language of kilograms. So I take my statement of equality, I put what I've been given, my grams, and I put it, that portion of the statement of equality in the denominator, in the bottom. I take the units that I'm going toward, what I want to end up in, and I put that in the numerator. I want to have kilograms, and it says that 1 kilogram is equal to 1,000 grams. Do you see conceptually that 1 kilogram divided by 1,000 grams is equal to 1? Because a kilogram is equal to 1,000 grams. So divide them by each other, conceptually, it's a 1. If you multiply anything by 1, you get itself, right? But in this case, since we're converting the language from grams to kilograms, the units matter. Now, look at the math. First, do the units. I have grams times kilograms divided by grams. Do you see that grams cancels grams and leaves me with kilograms? Okay. So when I do this math, whatever the numbers work out to be, my units for this answer are going to be kilograms. Is that what I'm looking for? I am. How many kilograms? Since I know the units work out, now I'll actually spend the time to do the math. 9,321 times 1 divided by 1,000. You know, you shorthand that, divided by 1,000, that makes that 9.321 times 1, 9.321. What are my units? Grams cancels grams to kilograms. So we now know that 9,321 grams is equal to 9.321 kilograms using the Factor-Lable Method. Go ahead and take a moment and work 1, 2 in your notebooks for a moment. Let you get a head start on me, and then we'll do it together. Don't worry so much about getting the solution, the answer. Just get the steps down now. Just to try to affirm in your mind that you understand process. Start learning the process. And that process is going to start by reading the question. So if a glass contains 0.465 liters of water, what is the volume of water in milliliters? I'm given what? I'm given, my known is a volume of 0.465 liters. It's the problem gave me. This is what you need to know. This is what I have. Somebody says, how do you know that? The problem gave it to me. How do you know it's right? Don't care. God wrote the book and said, you have 0.465 liters. Okay, now what's your unknown? What is the volume in milliliters? Right. Later on, we'll get much more complex in terms of we've got something and we need to convert it to something that's going to take you multiple steps to get to it. But for now, or even then, the process is going to be the same. Known, unknown, process. So I was going to start with, I know that I have 0.465 liters, and my unknown is, what is that in milliliters? Statement of equality is that 1 milliliter is equal to 1/1000th of a liter. You could have written that 1,000 milliliters equals 1 liter, and the math will work out the same. But to keep it consistent with the book, we learned that milli means 1/1000th, and therefore we replace the 1/1000th with 1/1000th. So it's 1/1000th of a liter. Now that I have my statement of equality, what's the setup going to look like? Just, don't worry about the numbers now. What's it going to look like? It's going to be a given or known times what? The known or given times my conversion factor to give me my wanted. My given to my wanted or my known to my unknown, same thing. My known times a conversion factor to give me my unknown. Question is, what is that conversion factor going to be, and where does it come from? Statement of equality, which is going to be what? Right there, right? So when I do the math, my given, my known, is 0.465 liters times one of these over one of the other one. It's going to be this over this or this over this. How do I know I set it up right? Because the units I want to end with, in this case milliliters, is in the numerator. It's on the top. So I look for the units in my statement of equality. Milliliters. Oh, see, I even wrote it down the other way around because that's the way I tend to think. So 1,000 milliliters equal to 1 liter. That's true. It could also be, up here, 1 milliliter is equal to 1/1000th of a liter. But you know what? The math is the same. If you take 1,000 divided by 1 or 1 divided by 1/1000th, it's the same number. So it's two ways to write the same thing. So you've got a known times a conversion factor with the units I want to end with in the numerator, so that liters cancels liters and leave me with milliliters. So it's right. And then 0.465 times 1,000 divided by 1 is equal to 465. And lastly, real rapidly, let's talk this one through quickly, and then we're going to hopefully give you an opportunity to work some in pairs. But on your own 1-3, on a professional basketball court, the distance from the three-point line to the basket is 724 centimeters. What is this distance in meters? I have a known distance of 724 centimeters. I look at the word problem and I try to find, okay, I'm given this, what am I looking for? What does the problem say we're looking for? Yes, ma'am. That same distance in meters. How many meters is 724 centimeters? So I have a given or a known and my unknown. How am I going to get from my known to my unknown? I need a statement of equality. What is that statement of equality going to be? I look at my units. I need some statement of equality that on one side of the equal sign has centimeters and on the other side of the equal sign has meters. What do we know that relates centimeters to meters? Just give me one. What's true about a certain number of centimeters and a certain number of meters? Yes, sir?
There's not 100 centimeters in 1 meter.
Okay. There's 100 centimeters in 1 meter. I, of course, did it the other way around, that a centimeter is 1/100th of a meter, because centa means 1/100th. Okay? So 1/100th of a meter. So if 1 centimeter is 1/100th of a meter, is that true? If it's true, I can use it for a conversion factor. I can create one by either putting 1 centimeter divided by 0.01 meters or 0.01 meters divided by 1 centimeter. Which am I going to put on the top?
On the top will be meters.
Meters, because that's the unit I'm driving toward. That's what I want to end up with. So 724.0 centimeters, my given or my known, times my conversion factor with meters in the numerator. Yeah, sorry about that. My mind goes back and forth between these two, but this is true as well. 1 meter is equal to 100 centimeters. Okay. Centimeters cancel centimeters, and I'm left with meters. That's the units I want. So I'd write meters down on my answer sheet first. That's what I would do. I go, okay, centimeters cancel centimeters. I'm left with meters. Meters, is that what I'm looking for? Yes. Okay. M goes on my answer. Leave room for my number, my coefficient. Then go through 724.0 times 1 divided by 100 gives me 7.240. And we'll get to this later in the module. It matters to have the 0 at the end. It matters. You'll learn later in this module when it matters and how it matters. But for right now, just so you know, 7.24 and 7.240 do not mean the same thing in chemistry. It communicates additional information. And what that is, again, we'll get to that in a few minutes. So we're going to move on now to converting between unit systems. Converting between unit systems. And frankly, it's pretty simple because all we're going to use is the Factor-Lable Method, creating conversion factors from table 1.3 in your book. This is not something that you need to memorize. So don't replicate 1.3 in your notes. Don't worry about writing this all down. But these are the statements. This is where we get our statements of equality for converting between the English system and the metric system. Okay. So whereas before we worked completely within the metric system, so everything was a base 10 relationship, right? It's either 1 times, 10 times, 100 times, 1/10th, 100th, 1,000th, and so on. Now we're going to get into kind of some different relationships. Remember, I said it's not quite as simple when we were using the English system. That means it's not quite as simple as when we convert back and forth between the metric and the English system. So measurements, distance, 1 inch is equal to 2.54 centimeters. You're going to be able to refer back to this table in your book when you do these problems. And if you did this on an exam, these numbers would be given to you. So don't worry about memorizing them. 1 slug is equal to 14.59 kilograms. And a gallon is equal to 3.78 liters. Okay, so that's great information to know. So how are we going to use it? Well, look at example 1.2 in your book. It starts at the bottom of page 12. It says that the length of a tabletop is measured to be 37.8 inches. What is the length in centimeters? Okay. So just as we did before, we look at the problem and say, what have I been given? This is completely worked out in your book, just so you know, in case you're feverishly writing. On page 12, everything is in there. It's just showing it up here on the front so we can look up here together. So if you need to refer back to it, it's laid out in your book. So my given or my known, my length is 37.8 inches. What is my unknown? What am I looking for? The question says, what is the length in centimeters? So again, working at the problem, my known, my unknown, my given, my wanted, same type of thing. But notice the difference. Now I've got to have a statement of equality that has inches on one side and centimeters on the other side. It's not as straightforward as the prefix, right? There's got to be some relationship that we need to know. And if you look at table 1.3, inches and centimeters, I have a statement of equality given to me that 1 inch is equal to 2.54 centimeters. There's my statement of equality. That's the key, the Rosetta Stone for converting from the language of inches into the language of centimeters. So I'm going to set up the problem just like I did before. I'm going to give my given, or my known, is 37.8 inches times a conversion factor. Looking at my statement of equality, what has to be in the numerator? It has to be what I'm driving for, right? I'm going to centimeters. If I look over here, 2.54 centimeters, that has to be in the numerator. What was I given? My units were inches, so my inches portion of my statement of equality goes into the denominator. Looking at the units, inches times centimeters divided by inches. Let me go ahead and write that on the board just so we can see it vertically. Inches times centimeters divided by inches. If I gave you a problem like that with no numbers, just units, inches times centimeters divided by inches, what would my answer be? Centimeters, right. Inches cancels inches to leave me with centimeters. So in the same way over here, inches times centimeters divided by inches, my units are centimeters. And the math, now the coefficient portion, the part I get to do on the calculator or in your head, is 37.8 times 2.54 divided by 1. Well, 37.8 times 2.54 is equal to 96.012. 96.012 what? Centimeters. Okay, so here we've converted, rather than within the metric system, we've gone from the English system into the metric system. Clear as mud? Okay, good. Why don't you work in pairs on 1.4 and 1.5 for a few minutes, okay? Go through and prioritize the setup. Write down your given, write down your wanted, write down your statement of equality, write out the equation, and then after you've done both of those, for both of those problems, then go ahead and punch in the numbers. Because once we're all done with the setups, we're going to get back together and go over them. Make sure you as pairs understand the setup, okay? Like, Yes, ma'am.
So for our answer, will we write down all of these or just round up the 0.50 thing?
You can put it to 0.5 for now.
Okay.
Mm-hmm. 0.5 would be the answer.
Okay.
And I'll explain why probably tomorrow.
Okay.
But for now, just, you know, even if you wrote that whole answer down for now, you'd know you were doing it right. You'll hear that several times through chemistry this year. You'll give me an answer and I'll say that's true, but it's not correct. Because, for example, if you said 3, I would say 3 Smurfs. No, that's true, but not correct because it's not fully correct. Like in this answer here, there's the first answer has a coefficient point, and then it has a 0.5. You know, it has more decimal places on your calculator. The answer is a certain number, 0.5, and it's cut off at that point for a reason, but you don't know that reason yet. In the future, if you gave me an answer that was something 0.5032, it might be too many decimal places, but we'll explain why that is shortly. Yeah, there's a logic behind where you cut it off at. Because something 0.5 and something 0.50, they look the same, they're the same mathematically, but they communicate information differently.
So you always cut it off at the 100th place?
No, you don't. There's a formula for figuring out where you cut it off at. It's not really a formula, it's a logical process, and we'll get through that logical process later in this module. It's going to take a few more minutes because we do want to cover at least one more concept before the end of the day, but press on and finish up your setups. And if you want to be able to turn and just be able to see the board in it when you're done, especially the front row, just so you can see the front. I don't mind if you kind of stay grouped, you know, paired up for the rest of this class. Yes, sir? For process, use the division sign. Use something over something. For now, it's just going to be yours. You're not turning this in. But I'm just saying in the future, it's going to help you to get down the process pattern behavior, to form a multiplier. That's what we're getting at. You're forming a multiplier. So by putting units divided by units and numbers divided by numbers, you're going to start to see it as a multiplier. And later on, this might seem a little bit difficult. In a few modules, you look back and go, it's like learning your alphabet. Now you're learning how to spell words, you know. So this will become obvious, but for right now, I know it's not. Okay, I want to encourage you, remember that the on your own problems are completely worked out in your book. So I hope, like when we do them together, like right now, you're not looking back at the answers. But if you have any questions, the nice thing is you can go back to the back of the book and look at them. And the other nice thing is they use the more vertical method of making your fractions. So if the typing laterally kind of confuses you a little bit, you're used to seeing A over B, not A/B. On the answer key, they put it A over B, so you can see it a little more vertically if that helps you. Let's go ahead and walk through 1.4. We have a known mass of 8.465 slugs. Okay? The problem asks us to convert that into kilograms. So we're going from an English system into a metric system using our new table of inequalities, or excuse me, table of equalities. So our statement of equality is going to be that one slug is equal to 14.59 kilograms. From that, I should have created a formula which says 8.465 slugs times, I'm looking for kilograms, so I put that in the numerator, 14.59 goes in the numerator, one slug goes in the denominator. So when I do the math, I first look at the units. Slugs cancel slugs, I'm left with kilograms in the numerator, and that's what my answer needs to be in. So my setup is correct. If you did it wrong, if you had this upside down, what would your units be? If I had this upside down with slugs over kilograms, what would my answer be in? Well, it would be slugs times slugs, which would be slugs squared, divided by kilograms. Because this would be slugs over kilograms, right? So my answer would be something slugs squared per kilogram. And I look up here and say, is that what I'm looking for? No. So I know that something's wrong. It's probably my conversion factor is upside down. I flip it over and go slugs cancels slugs, leaving me kilograms. Yes, that's what I'm looking for. This is the right setup for the conversion factor. Then I go and spend the time to punch in the numbers in the calculator. See the difference? I can know that I've got the setup right because the units work. And then I check them, and 123.5 kilograms. 1.5, your volume was 6.1236 liters. Your unknown was, what is that same volume in gallons? So I need a statement of equality that relates liters to gallons, and I get that from the table as 1.00 gallons is 3.78 liters. Since I'm going from liters to gallons, my conversion factor then is gallons over liters. So it's 6.1236 liters times 1.00 gallons over 3.78 liters. Liters cancels liters, leaving gallons in the numerator. That's my answer, and that's what I'm looking for. It's set up right. Now spend the time on the calculator. 6.1236 times 1.00 divided by 3.78 gives me 1.62. Okay. Now the next section in your notes, 1.7, is going to more complex unit conversions and problem solving. Here's the deal between this. Up to this point, we've had a known times a conversion factor to give us our unknown, or a given times a conversion factor to give us our wanted. Okay? Now we're going to add another little spice of life to the whole deal and take it and double it out. Multiple conversion factors. See, up until now, the conversion factor has always been what I wanted over what I was given in terms of units. Now we're going to have to add this whole idea of an intermediary unit. Meaning, I've got a known, or a given, times some intermediary unit over my known. Well, if I just did that part of the math, known cancels known, and I'm left with the intermediary. See that? Then I need another conversion factor. And that other conversion factor takes me on the top to my unknown, or my wanted, divided by that intermediary factor. So I get two conversion factors. See, if you do the math, known cancels known, the intermediate term cancels intermediate, and I'm left with my unknown, or my wanted. So it's basically daisy chaining. So you're not going to convert from you're not going to convert from one thing directly to something else. You're going to convert from one thing to something in the middle, and then from that something in the middle to what you want. Because you can't memorize necessarily how everything is related to one another. So look at example 1.3 real quickly, and that is on page 14. So again, this is all written out in your book. It's up here so we can go through it together. It says an object is measured to be 0.030 kilograms. That's its mass. What's its mass in milligrams? Now we're staying within the metric system, but do you know off the top of your head a nice, easy statement of equality that has kilograms on one side and milligrams on the other? Probably not. But we do know that we're looking for the mass in milligrams. We do know some statements of equality that relate kilograms to something and milligrams to something. And do we know something that they both relate to? Well, we know a kilogram is 1,000 grams, right? And we know that a milligram is 1/1000th of a gram, right? Do you see that grams is going to be my intermediary term? I'm going to convert from kilograms to grams, and then convert from grams to milligrams. Take it as a two-step process. Because I don't know a statement of equality off the top of my head. I can compute one, but I don't know one off the top of my head that takes me from kilograms directly to milligrams. So I need two steps. So it's set up the same way. My intermediary term, my middle term, the halfway point is grams. I'm going to go from kilograms to grams, and then from grams to milligrams. And here's what it looks like. My given, my known, is 0.030 kilograms times, I need to have a statement of equality that has kilograms in the denominator and my intermediary term, my middle step, my middle term in the numerator. I get that from 1 kilogram is equal to 1,000 grams. So it's my given kilograms times grams divided by kilograms. My units here, after I do kilograms times grams divided by kilograms, my units are going to be grams. Now I need to consider a conversion factor that takes me from my grams to milligrams. I need milligrams in the numerator and grams in the denominator. As you look at it, kilograms cancels kilograms, grams cancels grams, I'm left with milligrams, and that's what I'm asked to solve for. My setup is correct. If I had some other weird derived unit, if they didn't cancel out nice and neat, probably one of my conversion factors is upside down. I need to go back and fix it. But now that I've checked that the units cancel and give me the units that I'm looking for, now I invest the time in the calculator and punch it all out with 0.030 times 1,000 divided by 1 times 1 divided by 1/1000th. Well, hopefully you see that, when you do the math, when you're multiplying by 1,000, this is also by multiplying by 1,000, right? Dividing by 1/1000th is the same as multiplying by 1,000, so 1,000 times 1,000 times 0.030. So that's where we come up with 30,000 milligrams. I can't convert from kilograms to milligrams directly, but I take it from kilograms to grams and then from grams to milligrams by daisy chaining conversion factors. And you could do it multiple steps, just as many as you need to get to where you need to go.